Hey there, it's Shannon Matchick-Myers, and today we're looking at section 6.2 from the ZIL text, which covers solutions about ordinary points. So we're going to check out solutions of linear second-order equations in the form of a power series, whose center is a number x0 that is an ordinary point of the DE. So let's consider the homogeneous linear second-order DE. A sub 2 at x times y double prime plus a sub 1 at x times y prime plus a sub 0 at x times y is equal to 0. Now, if we get this into standard form, multiplying by 1 over a2 at x on both sides, then we will end up with y double prime plus a1 at x divided by a2 at x, y prime, plus a0 at x divided by a2 at x times y is equal to 0. Which we've looked at this before. That ratio of a1 to a2 is our capital P at x. Sorry about the dogs. And then that second ratio, a0 at x over a2 at x, is q at x times y equal to 0. So notice here, a2 at x is in the denominator for p at x and q at x. Cool? Okay, so definition 6.2.1, ordinary and singular points. A point x equal to x0 is said to be an ordinary point of the differential equation, the one we just talked about, if both coefficients p at x and q at x in the standard form, which we just derived, are analytic at x0. So whatever we are centering our power series at. A point that is not an ordinary point of that first equation is said to be a singular point of the differential equation. Note, a homogeneous linear second-order DE with constant coefficients can have no singular points, so that's nice. So every finite value of x is an ordinary point. Consider y double prime minus e to the x times y prime plus natural log at x times y. So this is already in standard form. Our p at x is equal to e to the x, and e to the x is everywhere continuous, right? That means it's continuous on all real numbers. So thus, it is analytic at all real numbers because we can use it in the power series. There's no discontinuities. But what about natural log at x? So q at x equal to natural log at x. Well, there's an issue, correct? It's not defined at x equals 0, so you can't make a Maclaurin series about it, a Maclaurin power series. So it can't be represented by a power series centered at 0. So, in other words, it can't be represented by a power series centered at x. Therefore, x equals 0 is a singular point for the whole dE because natural log at x is the coefficient to the y term. So x equals 0 is a singular point of the entire dE. Cool, cool? All right, now polynomial coefficients. We'll be focusing on the case when the coefficients a2 at x, a1 at x, and a0 at x, in that first equation we were talking about, a sub 2 at x times y double prime plus a sub 1 at x times y prime plus a sub 0 at x times y equal to 0 are analytic functions with no common factors. Since a polynomial function is everywhere continuous, it is analytic at any value of x, and a rational function, which is in the form of polynomial over polynomial, is analytic except at points where its denominator is 0. Therefore, p at x equal to a sub 1 at x over a sub 2 at x and q at x equal to a sub 0 at x over a sub 2 at x are analytic except at those numbers for which a sub 2 at x equals 0. It naturally follows that a number x equal to x0 is an ordinary point of a sub 2 at x y double prime plus a sub 1 at x y prime plus a 0 at x times y if a sub 2 at x is not equal to 0. Whereas x equal to x0 is a singular point of that same equation if a sub 2 at x equals 0. So we have to check for issues with the domain. Theorem 6.2.1, existence of power series solutions. If x equal to x0 is an ordinary point of the differential equation, the same one we've been dealing with, a sub 2 at x y double prime plus a sub 1 at x y prime plus a 0 at x times y equals 0, we can always find two linearly independent solutions in the form of a power series centered at x0. So that is, we can write it as y equals the summation from n equals 0 to infinity of c sub n, and instead of writing x minus a like we were in the last section, we're going to write x minus x0. Groovy? A power series solution converges at least on some interval defined by absolute x minus x0 less than r, where r is the distance from x0 to the closest singular point. A solution of the form y equals the summation as n goes from 0 to infinity of c sub n times x minus x0 is said to be a solution about the ordinary point x0, the distance r from the previous theorem is the minimum value or lower bound for the radius of convergence. All right, let's look at an example here. Find the minimum radius of convergence of power series solutions about the ordinary point x equals 0, and then about the ordinary point x is equal to 1. So first focusing on the ordinary point x equal to 0. So let's check it out, all right? And sorry, that would be x sub 0 would equal to 0. So we need to find out when a sub 2 at x is equal to 0. We need to find out when a2 at x equals 0. So what is a2 at x? It is x squared minus 2x plus 10, and then set that equal to 0. Well, this doesn't factor easily or at all, so I'm going to use that quadratic formula. So x is the opposite of negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 10 all over 2 times 1. And continuing, we will have x is equal to 2 plus or minus. That's going to be 4 minus 40. So the square root of negative 36 all over 2. And then we'll get x is equal to 2 plus or minus 6i over 2. We can divide out a 2 from each term. x1 then will be equal to 1 plus 3i when I divide out that 2. And then x2 will be equal to 1 minus 3i. Cool so far? All right, so these two are singular points of the differential equation. So if you take a look at, just a picture in the complex plane, so the I would be like the y-axis. So basically, let's see what we have going on. So we're going to end up having our x0 is equal to 0, right? So we've got this ordered pair 0, 0. And what we found right here is that this one would be graphed as 1, 3i. And the other one would be graphed as 1, negative 3i. So we would have 1, 3i or 1, 3. And then x0 is 0, so that's where we'd be looking at that distance, right? Because this is a singular point. And then we're also going to have another one down here. But they're going to be equidistant, right, from 0, 0. So this one would be the ordered pair 1, negative 3i, or 1, 3. So when we're looking at finding this distance, right, and this will help for our two solutions, then what we will do is the following. So let's check it out. We would have the distance would equal to the square root of 0 minus 1 squared plus 0 minus 3 squared. So then the distance would be the square root of 10. And so what does that mean? So again, we use the points 0, 0 and 1, 3, keeping it non-complex, right? And so that means that the absolute value of x minus x0, which is 0, has to be less than root 10, which is absolute x must be less than root 10. And so r is equal to root 10. Groovy? And two solutions exist. Each series must, so let's write this out. Two solutions must exist from that theorem, I think it was. And each series must converge at least for, maybe more, but at least for absolute x less than root 10. And so that gives us our radius of convergence is root 10. Just circle this whole thing. Cool, cool? Okay, now doing the whole thing over again, except for this time when x0 is equal to 1. So now it's going to be shifted over 1, right? So when we take a look at our A1, if we set A2 at x equal to 1, then we would have x squared minus 2x plus 10 would equal to 1, which gives us x squared minus 2x plus 9 is 0. And then again, solving, we'll have x equals the opposite of negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 9 all over 2 times 1. So x will be 2 plus or minus, that's going to be the square root of negative 32 over 2, which will be x equals 16 times 2 is 32, right? So we would have 2 plus or minus 4 root 2i over 2, and then that's going to give us that x will be, x1 would be 1 plus 2 root 2i, and x2 would be 1 minus 2 root 2i. And so these will be, so the points, so remember they're shifted over by 1. So that means that the points 2 and then 2 root 2 I, and 2 comma negative 2 root 2 I are singular points. Of the DE. So if I make another picture, right, this is what it would look like. You would have something along these lines. Now, since our center is now at 1, it's been shifted to the right by 1. And so everything is going to start here. And then this time 2 root 2, it's going to be a little bit more than 2. So this is I, 2I, 3I. And so now, instead of being centered at 0, it's centered at 1, 0, right? Or it's at the point that we're interested in, which is our ordinary point of the DE is 1, 0. So this is the ordinary point, 1, 0. So we're shifting to 2, because it'll be over 1, right? From the 1 plus 2 root 2I. So we're shifting over to 2, and then it'll be just above there. And then the lower one would be about here. And so these are the distances, right? So this ordered pair would be 2 comma 2 root 2I, or just 2, 2, right? Or 2 comma 2 root 2. And then this one is going to be 2 negative 2 root 2I, or working with 2 negative 2. Cool, cool? All right, so let's do this. We will have our distance this time is going to be, so we've got these points here, so it's going to be 1 minus 2 the quantity squared plus 0 minus 2 root 2 the quantity squared. So our distance will be 1 plus 8 under the square root, which is root 9, which just gives us 3. So, like we said, we'll just put on this one our radius of convergence is 3. And we'll get to solutions just like before. Groovy? Okay, so finding a power series solution. The basics are you substitute y equals the summation from n is 0 to infinity of c sub n times x to the n into the differential equation. You combine series. And then you equate all the coefficients to the right-hand side of the equation to determine the coefficient c sub n. Since the right-hand side is 0, all coefficients of x must be equated to 0. This does not mean that all coefficients are 0. Okay, so, and don't forget the constant terms, which are really multiplied to x raised to the 0. Okay, so let's look at an example. By the way, if you haven't seen the last video, you might want to at least look at the very last example. We did this for a first order DE, and I think it would be helpful. All right, so let's do this. Now, just a couple of reminders, all right? We're using y equals the summation as n goes from 0 to infinity of c sub n times x to the n. So y prime will be the summation as n goes from 1 to infinity. We looked at all this in the last section of c sub n times x to the n minus 1. And y double prime will be the summation as n goes from 2 to infinity of c sub n times n minus 1 times x to the n minus 2. We'll be using those for both examples that we have. And continuing, we will have y double prime, which is the summation as n goes from 2 to infinity of c sub n times n minus 1 times x to the n minus 2. And then plus x squared times the summation as n goes from 0 to infinity of c sub n times x raised to the n. And that's all equal to 0. So let's continue on. We'll have n equals 2 to infinity of c sub n times n minus 1 times x to the n minus 2. Plus, bringing the x squared into the summation, n will go from 0 to infinity of the summation, of c sub n. And when you bring x squared in, you'll have x to the n plus 2, and that's all equal to 0. Now, if you take a look at what we have going on here, I start out with, if I plugged in n equals 2 to this first summation, x would be raised to the 0 power. Now, if I plug in n equals 0 to the second summation, x would be raised to the second power. So what I'm going to have to do is I'm probably going to have to, pull out a couple terms from that first one, okay? But we'll go ahead and start making our substitutions. So remember, again, this is something we worked on in the last one. So for this one, I'm going to let k equal to n minus 2. That means that n is k plus 2, right? And when n is 2, k is 2 minus 2, which is 0. So that's where the summation would start. Cool so far? All right, now for the second one that we have going on, we're going to let k equal to n plus 2. That would make n equal to k minus 2. And when n starts at 0, k is going to start at 0 plus 2, which is 2. So rewriting these in terms of k, this is what we will have. The summation as k goes from 0 to infinity of c sub n, and n written in terms of k is k plus 2. And then we will have times k plus 2 and then we're going to have a k plus 2 minus a 1. That's for that first summation. And then what do we have left? We have x raised to the k. Cool, cool? Now for the second one, we will have plus k is going to go from 2 to infinity. We'll have c sub k minus 2 and that's going to be times x to the k. Groovy? All right. So now simplifying, working with this, we will have, and oh, that's all equal to 0. So we'll have this summation as k goes from 0 to infinity of, we'll have k plus 2 times k plus 1 when we simplify that second factor, c sub k plus 2 times x to the k, plus the summation as k goes from 2 to infinity of c sub k minus 2 times x to the k, all equals 0. Now we want both of these x's to be raised to the same power, so we're going to have to adjust the summation. Do you notice that when k is equal to 2 on the first summation, we would have an x squared? So we're going to find the first two terms. So our k equals 0 term, we plug in 0 wherever there's a k, and then we'll have 2 times 1 is 2c2, x to the 0 is just 1. When we plug in k equals 1, we would have 1 plus 2 is 3, 1 plus 1 is 2. So we'll have plus 6c3 x to the 1. And then plus the summation as k goes from 2 to infinity of k plus 2 times k plus 1 times c sub k plus 1 x to the k. And then plus the summation as k goes from 2 to infinity, c sub k minus 2 x to the k, all equal to 0. Now we need to get one happy summation now that everything is squared away. So we'll have our 2c2 plus 6c3 times x plus the summation as k goes from 2 to infinity. We're going to factor out an x to the k to the right-hand side. So we're going to have x plus 2 times x plus 1 times c sub k plus 1, and then plus c sub k minus 2 from the other factorial, all times x to the k equals 0. All right, good so far? So now let's go ahead and this whole coefficient would have to be equal to 0, as would the 6c3 and then the 2c2 separately, because the 2c2 is a constant term, 6c3 is the x to the coefficient to the x term, and then these are the coefficients to the kth term, x to the k term. 2c2 is 0, which gives us that c2 itself is 0. We will get 6c3 is 0, and so again c3 will be 0. Now we will have k plus 2 times k plus 1 times c sub k and you know what I just noticed? This should be k plus 2, k plus 2, My bad. And this is k plus 2. I think I caught it everywhere else. All right, and then plus c sub k minus 2 is 0. So isolating c sub k plus 2, because that's going to be further along than k minus 2, right? We're going to get 1 over k plus 2 times k plus 1. And that's going to be negative because we moved c sub k minus 2 to the other side. Cool so far? So now we're going to work with this one, all right? So working with our c sub k plus 2, all right, working with this here, let's see what we have. And don't forget about all this other stuff. We have C2 is 0, C3 is 0. We don't know so we're going to let, for this first one, okay, we're going to let C0 be 1. This is how you get two solutions. And C1 will equal to 0. We're going to do this all over again and switch it around to get our next set. And so working with this, we will have to get, and then remember k goes from 2, 3, ... So the smallest number we can plug in is 2 for k. So here we go. When k is 2, we'll get C4, and that will equal to negative 1 over 2 plus 2 is 4 times 3. And then that's going to be times c sub 4 minus 2. When k is 2, this will give us c sub 0. We let c sub 0 equal to 1, and so C4, so this will equal to negative 1/12 times 1, which is negative 1/12. Cool so far? All right. So C5 happens when k is 3. That's going to be negative 1 over 5 times 4. And then when k is 3, we'll get C1 here. So that's going to give us negative 1/20 times 0, which is 0. When k is 4, we'll have C6. That's going to give us negative 1 over 6 times 5. And then we'll have times C2, which will be negative 1/30. C2 was equal to 0. And then C7 occurs when k is 5. And we'll have 1 over 7 times 6. And when k is 5, this side will be C3. That is 0, right? So we'll have negative 1 over 42 times 0, which is 0. And then we'll finally get some sort of a trend going on when we get to C8. That's when k is 6. So this will be negative 1 over 8 times 7 times C4. That will be equal to negative 1 over 56 times negative 1/12, because that's what C4 was. And that in turn will equal to positive 1 over 672. So here we go. Y1 will then be equal to, we don't have to get a formula for this. We've gotten enough terms. Our very first is C0, right? And then we got everything zeroed out until C4. That'd be times x to the 4th plus C8 x to the 8th, etc. And so plugging in, C0 was 1. C4 was negative 1/12. C8 is positive 1 over 672 times x to the 8th. And then minus plus ... So that's our first solution. Now we get our second solution just by letting C0 be 0 and C1 be 1. And again, we work through it. So C4 will be when k is 2. And we're going to get the same stuff. We're going to get negative 1/12, okay, times C0. But this time, C0 is what? 0, right? So we'll get 0 for C4. C5 will still get that negative 1/20 times C1, but this time C1 is 1. So we'll get negative 1/20 for C5. C6 will be negative 1/30 C2. Well, that's going to zero out, right? Because C2 is 0, right? So that's just 0. C7 will be negative 1 over 42 times C3, but C3 is 0. And then C8 for this one will be negative 1 over 56 times C4, but C4 on this one is 0. So we'll just get 0. And then C9, I think we'll get somewhere. So C9 will be negative 1 over 9 times 8. And then times C5. C5 is negative 1/20. So we'll get negative 1 over 72 times negative 1/20. And that will end up giving us that C9 is equal to 1 over 1440. Cool? So Y2 is going to be C1 plus C5 times x to the 5th plus C sub 9 times x to the 9th plus ... So plugging in, we'll have Y2 is, and sorry, this would be C1 times x plus. Cool. 1 times x is x. C5 is negative 1/20 times x to the 5th. And then plus 1 over 1440 times x to the 9th. And then minus plus ... Groovy? All right. So we're all done with that example. And we've got one more waiting for us. So here we go. This one's going to be a little more complicated. So just bear with me. We'll be multiplying a couple power series together. So remember y double prime, same assumptions as with the other problem. So that'll be the summation as n goes from 2 to infinity of C sub n times n minus 1 times x to the n minus 2 plus e to the x times y prime. Y prime goes from n is 1 to infinity. C sub n times x to the n minus 1 minus y. which is the summation as n goes from 0 to infinity, c sub n times x to the n, and that's all supposed to equal to 0. So continuing, we'll have the summation as n goes from 2 to infinity of, I'll write it as n times n minus 1 times c sub n times x to the n minus 2 plus e sub x is itself an infinite series, right? So remember, you can look it up on that list. This is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... And then that's going to be times, let's stretch out this summation a bit. So we'll have 1c1 times x to the 0 just gives us c1. When n is 2, we'll have plus 2c2 x to the 1. And then when n is 3, we will have 3c3x squared and then I'll go to the same power of x. We'll end up with 4c4 x cubed plus ... And then we still have another summation hanging around. And all of that equals 0. So we're going to take these two and do a little bit of side work. Isn't that exciting? Exciting. All right, so we're going to copy it, I don't know, somewhere down here. We've got room. Paste. So we need to come up with this product, right? So that's going to equal to, you're distributing. So I'm going to take the 1 through all of that second factor. So we'll get c1 plus 2 times c2x plus 3c3x squared plus 4c4x cubed plus ... Now I'm going to take the x through each one. I'm going to line up the powers of x. So I have c1 times x plus 2c2 x squared plus 3c3 x cubed plus ... And then the next one, bringing the x squared through, we'll have x squared over 2 factorial. We'll end up having one half c1 times x squared. So c1 1/2 c1 times x squared. And then we'll have, the 2's will cancel out. So we'll have plus c2 x cubed plus ... So when we add these together, we're just going to go the first 3 terms to get to c4. So we'll have c1 plus, factoring out an x to the right, we'll have 2c2 plus c1, all of that times x, plus 3c3 plus 2c2 plus 1/2 c1 times x squared, and then plus 4c4 plus 3c3 plus c2 all times x cubed. Cool so far? All right, so now let's check out what we've got, all right? We'll bring this back over here and see what we've got, all right? So I'm going to go ahead and work out the first few terms of that very first summation. So we're going to have, when n, so I'll do it in this one here. So we started n as 2, and then we're going to have 2 times 1 c2 x to the 0. So we'll have 2 c2. Good so far? Plus, when n is 3, we'll have 6 c3x. When n is 4, we'll have plus 12 c4x squared. When n is 5, we will have, let's see, 5 times 4 is 20. So 20c5 x cubed plus dot, dot, dot. So we've got that one grouped. I'm going to paste the one we just figured out. So that's going to be plus all of this and then we're going to have minus and now I'll work this summation here. So when n is 0, we'll have c0 times x to the 0, which is 1. When n is 1, we'll have c1x plus c2x squared plus c3x cubed plus dot, dot, dot. Groovy? Okay, so now all of this, of course, is equal to 0. And now when I combine these, okay, so I'm looking at these expanded summations, all right? So when I combine these guys, I'm going to combine them by constants or together, and then we'll have, you know, the coefficients to x together, coefficients to x squared, etc. Ready? So let's do this. We will have the constants first. So starting with 2c2 plus c1 minus c0. Those are the constant terms that we've developed. Cool so far? And then plus, now the x term, 6c3 plus, put a different bracket here, 2c2 plus c1, and then minus c1, all times x. And then let's see what we have for x squared. We will have plus, I think they're going to get bigger, so I'll go here, 12c4, I'm the pink one, or purpley one, and then plus 3C3 plus 2C2 plus 1/2 C1, and then plus C2, no, minus C2. All of that is times x squared. And then the cubic will have 20C5 plus 4C4 plus 3C3 plus C2, and then minus C3 times x cubed equal to 0. And putting them together, we will have the constants stay the same, 2C2 plus C1 minus C0. And then the C1 zero out on those coefficients to the x term. So we'll get 6C3 plus 2C2 times x to the 1. And then we can combine the C2s. So we'll get 12C4 plus 3C3 plus C2 plus 1/2 times x squared. And then we can combine C3s on that last one. So we'll have 20C5 plus 4C4 plus 2C3 plus C2, all times x cubed is equal to 0. And this would just keep going on and on and on and on. I mean, these would keep going on. But we're just going to look at these so far. All right. So, I mean, just for the sake of form, we're going to say plus dot, dot, dot. And that's all equal to 0. Okay. So now you've got to equate each one of these bad boys to 0, right? So 2C2 plus C1 minus C0 equals 0. That's equating all the constant terms to 0. So isolating C2, we would have 1/2 times C0 minus C1. Now next up, I'm going to take 6C3 plus 2C2 equal to 0. And so C3 will equal to negative 1/3 times C2. Good so far? And then we've got our coefficient to the squared term, so we're going to have 12C4 plus 3C3 plus C2 plus 1/2 is 0. Isolating C4, we would have negative 1/12 times 3C3 plus C2 plus 1/2. And then I've got my 20C5 plus 4C4 plus 2C3 plus C2 is equal to 0. And that would give me C5 is equal to negative 1/20 times 4C4 plus 2C3 plus C2. Groovy? Okay, so now we want to get to solutions, right? So we have all these things going on. So we're going to be working with these right-hand sides. So if we let, in our first go around, we could let C0 equal to 1 and C1 equal to 0. So then that will give us, if we do that, looking at all of these things, then we'll have C2 is equal to 1/2 times C0 minus C1. So 1 minus 0, which will be 1/2. C3 will be equal to negative 1/3 times C2, which is negative 1/3 times 1/2, which is negative 1/6. C4 will be negative 1/12 times 3C3, so 3 times negative 1/6, plus C2, and C2 was 1/2, and I'm looking over here. You know what? That coefficient to this should have been 1/2 C1. My bad, from over here. So this would be 1/2 C1. And this will be 1/2 C1, but C1 was 0. And then plus 1/2 C1, and C1 is 0 in this case. So that is going to be what? This will be negative 1/2 plus 1/2 is 0. 1/2 times 0 is 0. So this will zero out, right? And then let's look at C5. This is going to be negative 1/20. We'll have 4C4, but C4 was 0, plus 2C3. C3 was negative 6. And then plus C2, which is 1/2. And let's see what shakes out. We'll have negative 1 plus 1/2 gives us negative 1/2 times negative 1/20, which I believe would be 1/40. Groovy? All right, so our first solution will be y1 equals C0 is 1, so we'll have 1, C1 zeroed out, plus 1/2, this is C2, so it'll be times x squared. And then C3 is negative, so we'll have minus 1/6 x cubed. C4 zeroed out, and then we'll have C5, 1/40 x to the 5th, and then whatever come what may. So here's one series solution. All right, so now we're going to switch it up. We're going to let C0 be 0 and C1 equal to 1. So when we do that, C2 will be 1/2 times 0 minus 1. So this will be -1/2. C3 will be -1/3 times C2 equals, and C2 was -1/2, well, I'll write it, equals -1/3 times -1/2, which will give us +1/6. C4 will be -1/12. We've got 3 times C3, which is +1/6 this time. And then, let's check back, C2. So what is C2? Is -1/2, so -1/2. And then 1/2 C1. And C1 is 1, so we'll have +1/2. So the 1/2s will zero out. I'll be left with a 1/2. So I'll get -1/24. See if I can move this down. All right, and then C5 will be equal to -1/20 times 4C4. So 4 times -1/24 plus 2C3 and then plus C2 and that's going to equal 2. Let's see, I'll have -1/6 plus 2/6 is +1/6. Minus 3/6 is -2/6, so I think -1/3. All right, so now our Y2 solution will be, so C0 is 0, C1 is 1, so we'll get 1x minus 1/2 x squared plus 1/6 x cubed minus 1/24 x to the 4th. And then actually I think I forgot to multiply this by -1/20. So we're going to get +1/60. So plus 1/60 x to the 5th. And that's our Y2. Cool? All right, so there you have it. This ends the video. Hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and hit that like button. Bye.